Hi, this is Physics 1, Physics 2, Chapter 30 and 31. Talking about physics and nuclear reactions. This is part 5, so we're getting into now fission and fusion. And so for fission, I kind of want to mention both the difference between these, just the names, fusion and fission. Fusion, if you fuse things together, you're taking two nucleuses and you're basically forcing them together into one big one. Not necessarily bigger, but you're forcing them into one. Fusion, you're taking one nucleus and you're pulling it apart into two different nucleuses as these are pulled apart. And we can kind of see that here, this was one and it's being pulled apart right there towards the center into two. So that is the difference between the two. The interesting thing is both will release energy, which is what's helpful. So one of the biggest questions we'll have here is why a neutron? Well, a neutron is not repelled by protons or alpha particles because it's neutral. It's also not repelled by electrons because it's neutral. And so a neutron is a lot more capable of reaching a nucleus. And so what we're going to do here is we're going to basically, we take a neutron, we shoot the neutron at a nucleus. Right, so this is the nucleus. And even with all these electrons around it, and we got protons in it, if this was an electron that we shot, that would repel away from these electrons. If this was a proton that we shot, it would repel away from these protons, or may even get stuck with one of these electrons. But this is a neutron, so it's going to ignore these, it's going to ignore the protons, and it's going to make it to the nucleus. So that's why we're going to look at using a neutron here. And so for fission, it's the split of the nucleus. The large nucleus splits into smaller parts. And what happens is with this split, it's going to release an extreme amount of energy. It's going to produce free neutrons. And because it's releasing energy and a high amount of energy, it's going to produce gamma photons. So what ends up happening with a nuclear fission is you'll get a chain reaction. And a lot of that has to do with the fact that you released more neutrons. So let's say we start out with one neutron being released. So we have this one neutron, it's coming in, it's hitting this uranium 9235 nucleus with 92 protons. So it's saying that, well, when it hits this, it splits this into two fragments. It also will release neutrons, right? And so one larger atom is going to split into two smaller atoms and release a lot of energy, as well as a couple of neutrons. These neutrons go and they find more nucleuses that they can hit. And when they hit them, they split those, releasing more neutrons. And then those neutrons go and they find, again, more nucleuses they can hit, and they'll hit more and split those, and when they split, they'll release even more neutrons. So you have all these neutrons going around, and now these are seeking out more and more nucleuses to split apart. And so we can look at it as, let me scroll down, a single neutron starting a whole uranium reaction. So this splits into krypton and beryllium, and a whole lot of energy is split and releasing all these more neutrons from it. And so how does this happen? Well, that nucleus is already unstable. Okay, it wouldn't necessarily happen with one that isn't unstable. So because it's unstable, by that added neutron, it's going to make it way more unstable where it can start pulling it apart. And the electrical forces within it become too big, the strong force isn't strong enough, and the nucleus begins to elongate until it just eventually splits. Okay, and these nucleons are in an excited state when this happens, and this extra energy caused an increase in motion, and this elongation just weakens the strong force because of it, and it's just enough that it can pull it apart. And so when it pulls it apart, it releases energy in order to it releases energy, it releases neutrons, and then we can harness that energy from it. Now, fusion is quite the opposite. And this is what happens in stars. So we have a whole nuclear fusion reactor in the sky, in the sun. What's happening there is you're having combining of particles. So we have one nucleus moving at a very high speed, and it hits another nucleus also moving at a very high speed. So you have these two nucleus moving at very high speeds, and they fuse together into one large atom. And usually it's going to be larger because usually, as we'll see through the elements of a star, you start out with the low ones like hydrogen, and they fuse into helium, and that fuses into carbon and so on. Or maybe lithium. I gotta look and see. So by it moving at very high speeds, they can overcome any kind of electrical repulsive forces and combine together and collide together, and because of that, fuse together as they collide. And so when you have this collision, most of the energy is kinetic energy, and it transforms into heat and releases tons of photons, which is just energy. And so we see those photons coming out of the star as light, and it lights up the earth and heats up the earth as it releases that energy. So let's look at an example here. We have a hydrogen atom that has one proton and one neutron. That's this one over here, the one blue and one green. Combines with a hydrogen atom of one proton, so proton is the green, and two neutrons, which is the two blues. They combine together into a fusion. Now, if we add this together, we have a hydrogen. Oh, let me get it. I want black. All right, so we have hydrogen with two and one proton. So we're adding together hydrogen with one proton and two neutrons, so three. And so if we were to just totally kind of think about this, we should have 5 and 1. Actually, I'm sorry, we should have 5 and 2. 1 plus 1 equals 2. We should have 5 and 2, and 2 would be helium. Okay, that's what we should have. That should be the total mass. Okay, but what actually will happen is this would actually transform. So this isn't what happens, and it actually becomes the helium, because this is a stable helium nucleus alpha particle, plus one neutrino, oh not neutrino, sorry, one neutron. So we have 1n, which is a 1 and a 0. And so we still have 2, we still have 5, but it splits like this instead of splitting like this. And when it does this, it's going to release a lot of energy. In the form of protons. Alright, so if we look at helium, oh not helium, I'm sorry. If we look at fusion in the sun and hydrogen, okay, we're going to start with one hydrogen combined with another hydrogen. And what you end up getting is I'm going to kind of do this in a couple of steps here. You'll get, now you have 2 protons and you have, 2 protons, no neutrons here, which will be hydrogen. But then this is going to convert one of the protons to a neutron. So this converts proton to neutron. And when that happens, you're releasing a positron. So we have hydrogen, mass number is 2, 1 proton, and then our positron, which is going to be 1 down here and 0. So this still has 2 and 2, okay? And then because you release the positron, you're going to release the neutrino. This whole reaction here is 0.42 MeVs of energy that's released. Then that will happen with this one here as well as this one here. So we're going to have this one done twice. So 0.42, and this is the first step. And then the second step will be another is the same step with different nucleus. And so 0.42. Different nucleus as in a different 2 hydrogens. So we have 2 hydrogens here, 2 hydrogens here. Alright, so then the next step is that these 2H, the ones that have 1 proton and 1 neutron, they're going to combine with 2 more hydrogens. Alright, and so now we're going through for this, you know what, no, I'm going to change the name of this step, 1B. We're going to call this next step 2 because I want it to align with these. So this step 2, we have 1 hydrogen, which is just 1 proton, plus our 1 here that we have. So 2, 1, and H. And that's going to combine together. You get 3 and 2, so you get helium. And then you get release of gamma rays. Okay, and this takes 5.49 MeVs. And so you have that in step 2, as well as 2B, which is going to be the same step with different nucleus. So you have another 5.49 MeVs. So we have one here, 5.49 MeVs here, and 5.49 MeVs here. Now these 2 nucleuses eventually, now they're helium, they're going to start combining together. And so when the helium combines with the helium, so you have 3, 2He plus 3, 2He So you have the 2 heliums from these 2 steps. So this one and the other one that goes with it. You'll get, well, let me add these together. I'm going to do a couple steps here. So you get 6 and 4 He. Well, actually, that wouldn't be He. It should have been K4 with that. That's not exactly He. So, or H here. So we're going to just call it X for now. Because I don't want to have to go through the whole what it would be. It doesn't actually become that, so I'm not going to write that down. But you'll have technically 6 and 4, which would technically be, it wants that alpha particle because it's stable, a 2 and 4 He, which means you have to release now 2 protons, which we'll just have it as, they have it as separate protons. So separate hydrogen atoms being released together, not combined together, but released together. And that whole reaction is 12.86 MeVs. Right, and so if we'll add these up, 12.86, we only have one of those, plus 2 times the 5.49, we have 2 of those, plus 2 times 0.42, so we have 2 of those, and we get about 24.6 there, 24.7 MeVs being released within this nuclear reaction. And so then these are going to go and combine with more hydrogens until eventually the sun's hydrogen will have transformed into helium, and then they'll start fusing helium together. And when that happens, we'll get into more detail in the last chapter of our class. Now, when it comes to the stars, so we also have in hotter stars where it has carbon and the carbon reactions. So carbon 12 with 6 protons, or 6 protons and 6 neutrons. When that combines with a hydrogen, you get a nitrogen, and then you get some gamma ray released, which would be a fusion reaction. Then that fusion, that nitrogen will go through a beta plus decay to get back down to carbon, and it releases a positron and a neutrino. So we get beta plus decay. Then that carbon will react with another hydrogen, and this will give you now a stable nitrogen nucleus, and you get more energy release, so you get a fusion reaction. And then eventually that nitrogen will react with a hydrogen, and you get an oxygen and gamma ray release, so you get another fusion reaction. Then the oxygen will go through a beta plus decay, getting down to hold on a second. Yeah, getting down to nitrogen. I just want to double check that I had something right. And releasing a positron and a neutrino. And so you have a beta plus decay. And then that nitrogen with 15, mass number 15, that's going to react with the hydrogen, getting back down to carbon and releasing a helium atom or alpha particle, and you have another fusion reaction. So it goes through this carbon cycle, and now we went all the way back down to carbon 12, so that's going to start reacting again with more hydrogens until all the hydrogen is gone. Notice that a lot of times the stable helium noble gas is usually where it ends. So for nuclear fission reactors, they're self-sustaining because of the chain reaction, and the neutrons from the fission reactions must be actually slowed down in order to really keep them self-sustaining. So they use things like graphite and water to help slow them down so it doesn't get out of hand. The neutrons may be absorbed by other nuclei within the reactor as well. So they can use light water to enrich the process and make it well that doesn't happen as often, and get more visible reactions to occur. Some neutrons can escape through the surface of the reactor core, so this requires a large amount of fuel because you're going to have some loss there. And the critical mass is the minimum amount of fuel needed to sustain the reaction. So the lowest amount of fuel you need to keep this reaction going and not dying out. There are possible fusion reactors, but none have actually been built. There's a lot of limitations to building these, as well as just being dangerous. And probably a lot of people against that even because of just how dangerous they are. But some of the ones that they look at to possibly build that would be hydrogen fusing with hydrogen, to get either a hydrogen plus a hydrogen with 3 neutrons plus a hydrogen. I'm sorry, hydrogen with 2 neutrons plus hydrogen with 1. You can also use it to get a helium plus a neutron, or to get a helium atom specifically plus a neutron, which releases the most amount of energy. Those are possible ways they could start to think about building a fusion reactor. Me personally, we have one in the sky. We got solar panels. I don't think we necessarily need to go about that route if we didn't have to. Alright, so that actually ends this chapter, which this the shortest video of them all. So I guess that's good. The next chapter is going to be, I don't think it's as much math as it is more kind of outlining of different types of particles, and then there's some math involved, but the math really is not what's hard. It's trying to remember everything, and when we get to particle physics, which is going to be good for you guys to take a test. Even in class, I think I would give you all the different particles and the details about the particles, but it's a lot to shift through, and they each have their own thing. But to be honest, it's one of my favorite chapters because I think it's really interesting. But it's also kind of one of those things that kind of really makes your mind explode. Alright, so I will see you in that chapter. And take care. Stay safe. Alright, bye.